Hello to everyone, welcome once more to another video in our YouTube channel. So as you can see, we are going to be looking at the competitive entrance examination into the National Advanced School of Post, Telecommunication and ICT in Yaounde, the 2021 session, specifically the mathematics paper. So as you can see, exercise 1 is on vector spaces. Those are the various questions. Exercise 2 is on probabilities. So that was the structure of the exam. Now we have the okay, so all right, now here's a continuation of exercise 2. That's probability. Now after that, we now get a problem where the problem is divided into 3 parts. So part A is on differential equations. There you can see. Part B is on the study of family of functions. And lastly, here's a continuation of part B. And then we have part C, which is on plane isometries. So that was a mathematics paper of the 2021 session of the competitive entrance examination into the National Advanced School of Post, Telecommunication and Engineering in Yaounde. We call it the Post or SUP'PTIC. Okay, so we are going to have a rundown of the paper. I'm going to solve some exercises which are very technical, especially exercise 1, which is on vector spaces. Exercise 2, which is on probability. I believe Anglophones, we don't face too much problems with probability as we do with vector spaces, so that's why I'm choosing vector spaces. Then later I might look at plane isometries, because it's also a new topic that was just introduced into the further math syllabus. Vector spaces is not taught at all in majority of the schools, so that's why I chose that to do. Okay, so I believe we can begin with the question on vector spaces. So I'm just going to begin with exercise 1. All right, so the question reads: let E be a vector space and B, Ij, the basis of E. Consider the endomorphism F of E with matrix. Here is the matrix of the endomorphism, where M is a real parameter. Number 1, for which value or values of M is F bijective? In this case, determine the matrix M inverse of F inverse. Okay, so like I said, we are beginning with exercise 1, which is on vector spaces. Alright, so we have an endomorphism. First of all, we should define the key terms. You have endomorphism. Endomorphism is simply a transformation that maps onto itself, meaning map all the points in the plane to itself. Now, the basis of the endomorphism has been given, and there we have E is a vector space. Now, this is the matrix of the endomorphism, and then M is a real parameter. Okay, first we need to determine the values of M for which the transformation F is bijective. So what does it mean for a transformation to be bijective? So there are 2 ways to do it, but in this case, we are going to do the shortest way. Now, to prove that, or to find the values of M for which this transformation having matrix this capital M to be bijective, we either use the null space of the matrix, or we use the concept of the determinant. So the null space is also called a kernel, meaning that a certain vector that maps to the 0 vector or to the null vector, or we use the concept of the determinant. Okay, so number 1, for F to be bijective, the determinant of M, which is that matrix, should be different from 0. So it means M minus 1, M plus 1, M minus 2, that's the determinant, should be different from 0. So it means that now this is 2 by 2 matrix. So to find the determinant, we do the product of the elements in the leading diagonal, and we subtract from the product of the elements in the non-leading diagonal. So we have M into M minus 1 minus M minus 2, minus m minus 1 into m plus 1 equal to 0. So this means m squared minus 2m minus m squared minus 1, that's just the difference of 2 squares, is equal to 0. So it means m squared minus 2m then minus m squared plus 1, different from 0, pardon. Alright, so we have m squared cancels m squared, and then we have minus 1 minus 2m different from 0, meaning that m is different from a half. So for all values of m that are different from half, our f is bijective. Alright, now next, in this case, determine the matrix m inverse of f inverse in base b. Now this our base is base b, so 2 dimensions. Okay, so now we need to determine m inverse in this case. So know that the inverse of m, so m inverse is equal to 1 over the determinant of m times the adjugate of m. So in this case we just have 1 over the determinant we have found. This is a determinant. The determinant is 1 minus 2m. 1 minus 2m times the adjugate. To get the adjugate of a 2 by 2 matrix, what we do is that we interchange the elements in the leading diagonal and we change the signs of the elements in the non-leading diagonal. So m minus 2 comes here, m comes here, so you have m minus 2, and then we change the sign of this. It means we multiply by a negative, so it becomes 1 minus m. Alright, here we also multiply by a negative, you get negative m minus 1, and then here we replace it with m. Alright, so we specify that m is different from half. So that's the inverse of the matrix m. Alright, now number 2 is asking us to determine m so that f is involutive. Okay, so we are determining m, small m, such that f is involutive. So if f is involutive, it's just the basic definition of the endomorphism. If f is involutive, then like we said, all inverses, all the matrices, the inverse of the matrix of the transformation is equal to the matrix of the transformation, meaning they are self-inverses. Okay, so with that we can get the inverse. Here's already the inverse here, so it means that 1 over 1 minus 2m times m minus 2, 1 minus m, negative m minus 1, and m is equal to the matrix itself. Here's a matrix: m minus 1, m plus 1, m minus 2, m minus 1, m plus 1, m minus 2. Okay, so you know how to do matrices. You just equate the corresponding entries. So we first of all multiply this factor into each of the entries. So here we are going to have m minus 2 over 1 minus 2m. We equate it to the m here. Now here we are going to get 1 minus m over 1 minus 2m. We equate it to this other entry here, which is m minus 1. Here we are going to get negative m minus 1 over 1 minus 2m, and equate it to this entry here, which is m plus 1. And finally we have m over 1 minus 2m, and equate it to this entry here, which is m minus 2. Okay, so from the first equation we have m minus 2 is equal to m into 1 minus 2m, equation 1. The second equation we have 1 minus m equal to 1 minus 2m times m minus 1. You can call it equation 2. The third equation we can divide all through by the negative sign. The numerator we get n plus 1 equal to m plus 1 times, since we divide by a negative here, we're going to have 2m minus 1. You can call it equation 3. And finally here we have m is equal to m minus 2 times 1 minus 2m. We can call it equation 4. Okay, so let's see what we can do to find the values of m. Remember that m should be different from half, so when we get half as answer we need to remove it, because if m is equal to half, the transformation f is not bijective, and hence it is not involutive as well. Okay, so we need to look for the value or the values of m. Sorry, we are looking for the value of m according to the equation. Okay, so let's see what we can do. The first equation, let's compare two equations together and we see what we can do. Okay, so let's just take the second equation from equation 2. we can take everything to the right hand side. We are going to get 1 minus m minus 1 times 1 minus 2m equal to 0. So it means that here we have 1 minus m plus, we can multiply this negative sign inside here and we're going to get m minus 1. So we are going to get 1 minus m, then times 1 minus 2m equal to 0. So we can factor out 1 minus m. From here we are going to get, from this place we get 1. Now from here we just get plus 1 minus 2m equal to 0. So this means that 1 minus m times 2 minus 2m is equal to 0, meaning that 1 minus m times 2 into 1 minus m is equal to 0. So we can conclude that our m is equal to 1, because 1 minus m all squared equal to 0, m equal to 1. So let's verify if m equal to 1 is going to satisfy all these equations. If m is 1 here, we have the left hand side is negative 1, the right hand side you have 1 times negative 1, perfect. So negative 1 equal to negative 1. If m is 1 here, here we have 0, here we have 0, so everything is okay. If m is 1 here, here we have 2, here we have 1 times 2. And if m is 1 here, we have 1, here we have negative 1 times negative 1, 1. So the value m equal to 1, then our transformation, our endomorphism f is involutive. Alright, now the third part, we assume m different from 0. So in this part, our m is different from 0. Show that there exists two values of lambda, two values lambda 1 and lambda 2 of the real parameter lambda, for which for any non-zero vector u of e, we have f of u equal to lambda u. We denote by lambda 1 the independent value of m. So now first of all, let's give the general expression of all endomorphisms. So our endomorphism is f. So what does it mean? It means that if I have a vector u that belongs to the vector space E, then f of u always be equal to the matrix of transformation, which is m times u. That's a representation of all endomorphisms, all linear transformations, let me put it that way. Okay, so according to this, we have that f of u is equal to lambda times u. What does it mean? It means that m times u will be equal to lambda times u, because our f of u is equal to m times u. Okay, so this means that here's our matrix m. So we have m minus 1, m plus 1, m minus 2. Now let's just see our vector u. Since our basis of E is this ij, so my vector u is going to be in 2 dimensions. Let me just put xy and I equate it to lambda, which is a real parameter, times u xy. Okay, so this means we can do the matrix multiplication. This times this plus this times is equal to lambda times x. So mx plus my minus y equal to lambda x, and then mx plus x plus my minus 2y equal to lambda y. Alright, so we need to find the values of lambda. Okay, so we clearly see that if we subtract the two equations, this will cancel this, my will cancel my, so we have negative y minus, so negative y minus x, then plus 2y, because we are subtracting negative 2y, to be equal to lambda x minus lambda y. So it means that negative, here you are going to get y minus x is equal to lambda into x minus y. Okay, so we can bring we can add this to the other side of the equation. We get 0 is equal to lambda into x minus y plus x minus y. Alright, so it means that we can factor out x minus y. We are going to get lambda plus 1 is equal to 0. So this means that x is equal to y, or lambda is equal to negative 1. But since we were being told that where is it, that lambda 1 is the independent value of m. It means that it does not depend on m, so we just specify that this is lambda 1. Now for x equal to y, we come back to maybe one of the equations here, x equal to y, equation 1, let's just label equation 1, equation 2. Our equation 1 means that here I'm going to put x with y, so I'm going to have my plus my still minus y is equal to lambda times y. I'm just replacing x with y, so it means that here we have 2my minus y is equal to lambda y. Since they told us that our, let's come back, they told us that our u vector is not null, for which any non-null vector u, you see, means that it cannot be 0, 0. So since it cannot be 0, 0, it means that this y cannot be 0. And since y cannot be 0 and x is equal to y, means that x cannot also be 0. So you can divide all through by y. We are not going to have any problem. So here we have 2m minus 1 is equal to lambda. So we specify that this is lambda 2. So it means lambda 2 depends on m. So we have shown that there exist two values of lambda, lambda 1 and lambda 2. So lambda 1 is negative 1 and then lambda 2 is equal to 2m minus 1. Okay, so we are rounding up with the equation. Now b, so this is 3a. b says we set f1 be equal to u, the vector u in E, such that f of u is equal to lambda 1 times u and f2 is equal to all of that. Roman 1, show that f1 and f2 are vector lines. Okay, so the b part, we have f1 being equal to u vector in our vector space, such that f of the u vector is equal to lambda 1 times the u vector, and then we have f2 equal to the u vector in our vector space E, such that f of that u vector is equal to lambda 2 times the u vector. Now we are showing that they are vector spaces. Okay, so let's first of all come, our f of u is equal to m times u, equation 1. We even saw it earlier. In this case, our f of u also is equal to lambda 1 times u, equation 2. So equation 1 is equal to equation 2 because f of u is constant. So it means that m times u is equal to lambda 1 times u. Remember, our u vector is the xy. So this means that, remember that our m is different from 0. So m times u, we can just come to this system, yes, and then we just replace the value of lambda with lambda 1. And our lambda 1 is negative 1. So let me just come here and replace, I write the very system that just replace lambda with lambda 1, which is negative 1. So it means mx plus my minus y is equal to negative x, and then mx plus x plus my minus 2y is equal to negative y. Okay, so we can see subtract both equations. So that's what we have. We can see subtract both equations. So let me just say this is equation 1, this is equation 2. If we take equation 1 minus equation 2, what do we get? This cancels this cancels this. So we have negative x minus y. So negative y minus x, then plus 2y equal to negative x minus negative y. So it means that negative x plus y is equal to negative x plus y. Alright, so negative x plus y is equal to negative x plus y. So it means that yeah, so from here I think we have made an error somewhere. Let's just verify clearly and see. Okay, so mx plus my, we replace lambda with negative 1, yes, and then we have that. Okay, anyways, it means that the equation is true, so this is not really advisable to do. So let's just deal with one equation and we see what we are going to get. So equation 1 means that mx plus my minus y is equal to negative x, because we arrived here meaning that this system is true because this is equal to this, but we cannot conclude anything about x and y. So let's just use one equation to find x in terms of y, and then we express our f1. Alright, so this means that we can pair the x together. Mx, we add x on both sides, plus x equal to y minus my. So out x, you get plus 1 equal to 1 minus m. So what's x equal to is 1 minus m over m plus 1 times y. So my u vector, which is xy, will now be equal to, in the place of x I put 1 minus m over 1 plus m times y. In the place of y I put y. So I can factor out y. I'm going to get 1 minus m over 1 plus m, and then 1 here. So it means u is a span of vectors. So my u vector in this case, let me just specify u1. That's for lambda 1 equal to negative 1. So it's going to be the set of vectors 1 minus m over 1 plus m, and then 1. Let's specify that alpha is a real number. So my f1 is now this span of vectors, this 1 minus m over 1 plus m. Because our y here is a parameter, so I just replace it with alpha and then 1. Yes, so I have something like this. Okay, now this guy here is simply because, so this u vector here, there are infinite number of them because this is it, you see. But this particular vector here is called the generator of the u vector, or the basis of the u vector, because it is from this vector here that we built other vectors under u, because alpha here is a parameter. Okay, now we can just conclude, because f1 is a span of vectors. So f1 is a span of the vectors u, and we are in the set of r squared, since the basis of the vector space is ij. So since f1 is a span of vectors in r squared, then it is a vector line automatically. Then f1 is a vector line. So we do the same thing for f2. Now f2 was defined, here is f2. For f2 is the same thing as f1, but now we are using lambda 2, and we got our lambda 2 as 2m minus 1. Okay, so for f2 is equal to, you have all the set of vectors u in the vector space such that f of u2 is equal to lambda 2 times u. Okay, now since you know that f of u is equal to lambda 2 times u, and f of u is also equal to m times u. This means that m times u is equal to lambda 2 times u. So we can just come and recopy our system of equations that we had earlier. So let's just copy back this system. We just replace lambda here with the value of lambda 2, which is 2m minus 1. Okay, so that system, we have mx plus my minus y is equal to, in the place of lambda we have 2m minus 1 times x, and here mx plus x plus my minus 2y is equal to 2m minus 1 times y. So this equation 1, this equation 2. Okay, so we can just deal with equation 1. So equation 1 means that we have mx plus my minus y is equal to 2mx minus x. So this means x minus 2mx mx, then plus my minus y is equal to negative x. Alright, so negative mx, you can add x on both sides, and then we send y minus my on the other side. So we can factor out x, we get 1 minus m equal to y into 1 minus m. Alright, so this means that you are going to get x equal to y. So that's what we are going to get. Our x is equal to y. So with that, it means our vector u, which is xy, is our x is y and then our y is y. So you can factor out y and we get 1, 1. So it is now a span of vectors still, maybe a parameter beta 1, 1. And we precise that beta is in the set of real numbers. So my f2 is span of vectors of u's 1, 1. So f2 is a span of, let's specify that is u2 in r squared, since the basis of our e is this. That's why it's saying it's r squared. So f2 is a vector line. Okay, so guys, sorry for being fast. It's just that I'm in a haste, so I just pray that you see what I'm doing and you understand what I'm doing. All right, so let's complete the equation. Roman 2 says let E1 be the basis of F1 and E2 be the basis of F2. Show that B prime, which is E1, E2, is the basis of E, and then determine the matrix of M in this basis. Okay, so we have Roman 2. E1 is the basis of F1. It means that now let's go back to our F1. This is our F1, you see. So this is a basis clearly, because it is this particular vector that brings up all the vectors in U. So it means that this is a basis. So our E1 is going to be 1 minus M over 1 plus M and then 1. And then now our E2 is a basis of F2. Now this is the basis of F2, 1, 1. So you have 1, 1. Okay. Now, what are we to show? We have to show that B prime, which is E1, E2, is a basis of E, and then we determine the matrix of M in this basis. So to show that B prime, which is E1, E2, is a basis of E, there are two things we need to show. The first is that E1, the set of vectors E1, E2, are linearly independent, and then the second thing is that E1, E2 are the generators, meaning the bases are the generators of F1 and F2. So clearly, since generators simply means basis, then it means that automatically this is already clear. So the second condition is satisfied. So you just need to show that the two vectors E1 and E2 are linearly independent. Okay, so for two vectors to be linearly independent, there are two things. It is either, let's just say M equal to the matrix, or let's say M1, the matrix formed by the two vectors E1 and E2. Here is E1, 1 minus M over 1 plus M. So the determinant of this matrix should be different from 0. If this matrix from 0, then and E1 and E2 are linearly independent. But if it is equal to 0, they are not linearly independent. So that's the first case. That's the first thing. I will show you another method. So the determinant of M1 is just equal to product minus this. We have 1 minus M over 1 plus M minus 1, which is 1 minus M plus, minus 1 plus M, all divided by 1 plus M, which is equal to 1 minus M minus 1 minus M, all divided by 1 plus M. So we have minus 2M over 1 plus M. So remember that in this particular equation, in equation 3, we're being told that what? That M is different from 0. We are assuming. Anyway, so this is the assumption D. So assumptions are very, very important. Alright, so since M is, because we know that this is a ratio of two things, you see. So for this ratio to be equal to 0, we just need the numerator to be 0. But since the numerator is different from 0, then it means that the determinant of M1 also be different from 0. So it means that E1 and E2 are linearly independent. Secondly, you can show that for every constants alpha and beta that are in the set of real numbers, alpha E1 plus beta e2 is equal to 0. That is equal to the 0 vector, and alpha is equal to beta equal to 0. All right, so alpha e1, we have alpha, this e1, 1 minus m over 1 plus m and then 1, plus beta e2, 1 1 is equal to 0 0, because we are in 2 dimensions, that is 0 vector. So it means alpha into 1 minus m over 1 plus m plus beta is equal to 0, and alpha plus beta is equal to 0. Alright, here alpha will be equal to negative beta, clearly, and then now we can replace alpha with negative beta. We have negative beta into 1 minus m over 1 plus m plus beta equal to 0. So alpha equal to negative beta, we can factor out beta from the numerator. We get I will write the component here 1, then minus this component 1 minus m over 1 plus m equal to 0. So it means that here beta will be equal to 0, or 1 minus this is the same as 2m over 1 plus m equal to 0, and then here alpha will be equal to negative beta. But for this to be 0, then the numerator needs to be 0. But since m is different from 0, then this automatically is different from 0, and beta is 0, so it means that alpha is equal to 0. So it means that they are linearly independent. And finally, what do we need to do? We need to determine the matrix of f in this basis. So the matrix of m in this basis is already this matrix here. So our m1, which is the matrix of f in that basis, is just equal to 1 minus m over 1 plus m, and then 1, and then 1 1. Alright guys, so that was all about question 1. Sorry if I never explained very well, but just that I'm in a haste, and I think there are students who need these solutions to prepare for the exam tomorrow, because the 2022 section is going to be written tomorrow. Alright, so if you have any question concerning any problem here, you can always comment on the comment section. I'm always going to reply to you. So that was it about the question on vector spaces. So see you in the next question. Probably we are going to do plane isometries. Yes, we are going to do plane isometries, because I believe so many students are also going to face difficulties in this particular question. Alright, so see you in the next video on plane isometries later in the evening.